Hi, this is Pt.1 and this is a quick review on the chapters of vectors, part 1. To start off with, we'll go through some of the definition and notation before moving on to some of the techniques involving vectors and methods such as addition, vector additions, dot product, cross product. Okay, without further ado, let's jump right in. So, vector is defined to be a mathematical object that has both magnitude and direction. So, it has magnitude and it has direction. If the quantity only have a magnitude, it is called a scalar. Okay, and one example in our day-to-day life would be velocity. So if we talk about a plane, let's say, having a velocity, we know that we must include both the speed that the plane is traveling at and the direction it is traveling at, whereas the speed is just how fast it's going, right? So that's an important distinction. So because there is a direction involved, we know that a vector must exist in some kind of space. Like it can either be 2D or a 3D space, and it's pointing somewhere within this space. Now, it's actually vectors in general is a very geometrical topic. So you visualize like where it goes, etc. A vector is notated as a arrow AB, or a bolded letter is represented as a line with an arrow. Within vectors, there's a type of vectors called the unit vector. It's basically a vector with length 1. I also like to think of it as having a vector with basically only direction. Because magnitude is 1, it's just a unit vector there. Doesn't tell us much about how long the vector is, it tells us the direction. Actually, that means a vector can be split into, because we know it's made out of its magnitude and its direction. So the magnitude is also something like a scalar. It's the same as a scalar, whereas direction is like a unit vector. That's how I like to think of it. Okay, unit vectors in the x, y, z direction is labeled as I, j, k respectively, usually, typically. Sometimes it's x, y, z. And when we are writing it, we must remember to write the hat. Okay, unit vector, when we write it out, is usually notated with a hat on top. For general vector, if we want to find the unit vector of it, we just take the vector itself divided by its magnitude. Because once we divide it by its magnitude, remember, we said the vector is composed of its magnitude and direction. So when we divide a vector by its magnitude, we are left with the direction, right? Mathematically, so previously all we have done is a very intuitive and visual way of seeing what vectors are. Actually, a lot of things in vectors, you will need to learn both the visual way of thinking about it and the mathematical way so that you can calculate things and you can solve the problem faster. Now, a mathematical way of representing a vector would be typically represented in a column of numbers. Well, what this column mean, right? So this column here, this column here. What this column mean is that your vector basically is traveling x in the first direction. Usually this first direction is x, y in the second direction, usually y, and z in the third direction. It's a bit hard to draw a 3D representation, but I will just do a 2D one to show what I mean. So let's say I have a vector v equals to 3, 5. So this 3, 5 right, means that first we move 3 in the x direction, then we move 5 in the y direction, and this is the vector v. Okay, this 5, this 3. This 3, this 5. Okay. We can also then write it in terms of unit vectors because we notice that we are traveling 3 unit in the x, which is 3i, and 5 unit in the y, which is 5j. So we can write it in terms of unit vectors as well. To find the modulus of a vector, we can use Pythagoras theorem. Pythagoras theorem extends beyond just 2 dimensions. It also works for 3 dimensions like this. So x squared plus y squared plus z squared, in which x, y, z are the components in each direction of the vector. And then you square root it, you get the length of this vector. This is very important. Please remember and learn how to apply this. It's simply just taking all the components and squaring it, square root, then we get the magnitude. When we have many vectors, we also encounter cases where vectors looks the same. To confirm whether if they are really the same, we need to show that they have the same magnitude and direction. Same magnitude and direction is one way. The second way is to prove that they have the same component. So if let's say I have a vector that is 1, 2, 3, another vector we show is also 1, 2, 3. We managed to show that it's 1, 2, 3 also. Then these two vectors are the same, right? So these are what we consider equal vector. When we have negative vector, it's actually basically they are equal, but all of their components have a negative sign. So an example of a negative vector would be -1, -2, -3. This can also be written as -1, 2, 3 like this. So whatever number that is outside of this vector will be multiplied to every component inside this vector. This is one thing to take note about the notation. And then we can talk about scalar multiple. Okay, I just talked about whatever number can be multiplied inside. So we can also multiply, let's say 3, 1, 2, 3. Then this will give us 3, 6, 9, like this. This vector 3, 6, 9 will be a scalar multiple of the vector 1, 2, 3. Okay, 3, 6, 9, scalar multiple of 1, 2, 3, because you can obtain one from another by multiplying it by a constant. Of course, if the constant that you multiply is negative, then we'll end up having in the opposite direction. But if not, you'll be pointing in the same direction. The scalar multiple of a vector is parallel to the original. When we multiply a vector object by 0, then we end up with a 0 vector because all the components just turn into 0. Then in that case, the vector is just nothing, it's just 0. So that defines our 0 or null vector. Finally, we talk about collinearity. So in here, we see that AB equals to BC, right? BC is a scalar multiple of AB. But we notice that they share the same point B. Okay? It may not be super clear earlier, but here the AB, right? A represents a point, B represents a point, whereas AB with the arrow just represents the vector going from A to B. So in this case, when we have AB equals to BC, right? We notice they share the same point B. That means we have a vector looking like this and a vector looking like this. Point A here, point B here, point C. And what do we notice? They lie on the same line. If they lie on the same line, we call that collinear. And this is what collinearity is about. With that, we covered all of the definition, all the definition that you should need to know. We then move on to manipulating vectors. Okay. When we have two vectors, we can actually just add them up like this. So here is A, point B. And let's say we have point C. Then when we add them up, the resultant vector is just simply when we join A to C. There's the outcome. You notice this forms a triangle. And that's why it's called the triangular law of vector addition. When we have multiple vectors that we want to add together, then we can just simply extend from there. One thing to take note when we are applying this triangular law is that we must always connect tail to head. So notice this is the tail, this is the head. We must always connect tail to head. So if let's say we have let's say we have two vectors UV. The resultant vector, we cannot just simply connect these two lines and tell me that this is the resultant vector. We must always travel according to the vector from tail to head. So in this case, we must shift this V to maybe here, and then we join from the tail of the first vector to the head of the second vector. And this is the vector addition U plus V. Okay? So always remember, when we add vectors, we join tail to head. You may have heard of another method called the parallelogram method, which initially does not seem like you need to join tail to head, but actually it's also the same thing. You also have to join tail to head if you do it properly. So let's say the parallelogram method will look something like this. U, V, then you go and draw the parallelogram like this, then you join. But actually you notice that in the process of drawing the parallelogram, right, you are essentially joining from tail to head again. Here is actually V, right? So actually we are still joining tail to head. So no matter what you do, right, you must always pay attention to this. Make sure you do not join the wrong vectors up. Yeah, so going back to adding multiple vectors, we see that when we try and add multiple vectors, it's the same thing, tail to head, and then we join the initial to the final, the initial tail to the final head. Essentially, vector is telling us like where to go. So like, Of course, you want to go like from one direction to another, following an arrow. Then if the arrow points backwards, then you know you probably did something wrong. Okay? Moving on. So that was the graphical way of dealing with vector, or the visual way of dealing with vector. Remember, we said that learning vector, you have to learn both the visual way and the mathematical way. So now we look at the mathematical way. Mathematical addition of vectors is very simple. You are just adding up the component in each component. So let's say we know that AB equals to x1, y1, z1, CD equals to x2, y2, z2. Then we just, in each component of the final vector, we just add the two components up. So it's quite straightforward. And then we talk about, and then when we have a mix of two vectors, okay, this is called there's a ratio theorem lah. This is just called the ratio theorem. So when we have 2 points, A, B, and they join a line, they form a line, and we have a point on the line that we're interested in. We know that this point has a ratio of mu to lambda from A to B. In this case, we can actually find the position vector of P. Position vector is just what's the vector of the point from the origin, right? So we see that to find it, we use this equation, and the way to understand this equation is just that we know that it's along the line, so we can represent it as a mix of A and B. But how do we mix A and B? We notice that P is mu away from A and lambda away from B. So in a sense, it's like, we can also think of it as P is mu closer to B, and lambda closer to A. So what we do is, we take the lambda and we multiply by OA, we take the mu and we multiply by B. Okay, in the current iteration of the notes, I believe there's a typo here. So just follow this video. I'll upload a new notes soon. Okay, and that's the ratio theorem. Ratio theorem is useful when we are looking at basically a point on a line that we do not already know what the vector of the point is. But we know the ratio of it to two known vectors. So we must first know what is OA and OB before we can find P, if we know the ratio. Yeah, and of course, in the equation, there's a divide by mu plus lambda. This is like, we are taking like the average. We know that if we are lambda close, mu close to we know that the weightage of OA is like lambda, and we know that weightage of OB is mu, but then we have to divide by like the total weightage. So it's like finding like an average of sorts. Okay, moving on, we have the direction ratio. When we have a vector that is A, B, C, in each of the component, the direction ratio is just A to B to C. This is just a fancy name. And we also have a direction cosine, which is again like a fancy name. I'll just draw it out graphically to show you how it looks like. So suppose we have a vector, and this is the x-axis. Okay, suppose we have a vector. This vector may not be in the x-axis. Okay, I'm just showing you the vector and the x-axis. We know that if we know the angle between the vector and the x-axis, then we can find the cosine. Right? This vector has the magnitude OP, and cosine A, let's say this is A. This has to be A because we know that the vector has A in the x component. So we can see that cosine alpha is related to A divided by magnitude of the whole vector. It's just like that. In a sense, it's like this direction cosine is just telling us like how much of the vector is in each component. So because it tells us how much of the vector is in each component, they must add to 1 if we go and Pythagoras theorem them. Then we talk about scalar or dot product. This is probably, along with the cross product, is the most important stuff that you need to learn in vectors. We denote them as A dot B with a dot in between, and this means like A, magnitude of A multiplied by magnitude of B multiplied by the cosine. In a sense, this is a bit like, okay, in a sense, graphically, this will look like this. First, we have A, this color. So we notice that we have a AB cosine theta, right? So we can visualize it as having A cosine theta. This tells us the magnitude of vector A in B, that is in the same direction as B. Then when we multiply this by magnitude of B, we can see that we are basically multiplying the component of A that is in the same direction as B with B. Then in the end, we get a scalar number. Of course, we can also visualize it the other way. And say that we are looking at the scalar component of B in the direction of A and multiplying it with the magnitude of A. Either way, it's the same. Okay? Now basically, a very intuitive way of thinking of dot product is it tells us something like how much of the two components are in the same direction. Okay? How much of the two vectors that are in the same direction. This can be very important because this tells us things like whether if they are parallel, perpendicular, things like that. Mathematically, you evaluate them like this. You take the first component and you multiply, you add, then you plus the second component, then you multiply, and then you plus the third component, and then you multiply. This will give us a scalar quantity, as you can see. There's no more vector in the final answer. So we talked about visual representation already. It's very important to understand this visual representation and to gain an intuition for it. But without further ado, let's jump into properties. So we see that because of how we define how the dot product is defined, we can see that we multiply the magnitude of A and B together. But if we multiply B with A, we still get the same answer because it's just a number. And that's why A dot B is the same as B dot A. It's also represented in what I talked about just now when we say that we can also think of it as B's component in A instead of A's component in B. Okay, like what I've just drawn. So another thing is dot products are distributive. If you do A dot B plus C, you can just think of it as A dot B plus A dot C. You can just break them up and calculate separately if it's more convenient to do so. If A dot B is 0, it suggests that either of the vector is 0 or they are perpendicular. If they are perpendicular, naturally they would not have a component of each other in their direction. So then in that case, the dot product will be 0. And finally, or not finally yet, if we have A dot A, we should get the magnitude of A squared because the angle between the vector and itself is 0 and cosine 0 is 1. In essence, you are basically thinking of what's the component of myself in my direction, and you will end up having just yourself multiplied by yourself. So this is quite a natural result. And finally, scalar multiples can be removed because we notice that if we look at the mathematical aspect of it, it's basically you are multiplying each of these by a number, let's say A, and then this A can then be factorized out of the sum. In a more graphical sense, it's like you are trying to multiply the length of the vectors. You're trying to make it a scalar multiple. Remember scalar multiple we talked about here? Yeah, here. So it's like we're trying to multiply a scalar multiple. We are trying to dot product scalar multiples of vectors together. Then you can just multiply the final result. It will be the same thing. For applications, I think I briefly mentioned it just now. It can tell us the length. Okay, start with length of projection, right? So it can tell us how much of the component of one vector is in the other. This is called the length of projection. Of course, to find the length of projection, we must divide by the magnitude of the other vector, which is why we write in terms of its unit vector in this case. So we know that A dot B is equals to A B cosine theta. We want to know what is A cosine theta. So we just divide this A dot B with a magnitude of B. Divide by magnitude of B and we get A cosine theta, right? So dot product is important to find length of projection. This is where you see the visual aspect of vectors merged together with the maths, because if you cannot really note, if you find it hard to visualize how the length of projection look like, it might be a bit difficult for you to see why dot product is so effective. Okay, try and think it through and visualize it if you cannot. It's quite important. Another application of dot product is that you can use it to find the angle between two lines or vectors. So we can see that a dot b is equals to the magnitude of a times magnitude of b times cosine. This also means that cosine of the angle between them can be represented in terms of the dot product divided by the magnitude. We know that dot product can be calculated by x1, y1, z1 dot x2, y2, z2, which gives us this number here. So, and we know that the magnitude can be calculated using Pythagoras theorem. So if we know the vectors a and b, we will be able to find the angle between the two of them. Okay? Notice that this angle is independent of the length of a and b. So if we are using unit vectors, this will work as well. As long as they are in the right direction, this method will work. Before we jump into cross product, I would like to briefly talk about this one last example of a real world application. So for those who take physics, this will be quite familiar to you. We know that work done is force times distance moved in the direction of the force. So let's say you have a person who is trying to drag a box. We notice that the force that the person applied to is not horizontal. It's actually slightly slanted, but the box is only moving horizontally. So the work done, right, we have to take a dot product of the force with the distance traveled to give us the final work done. Okay, and this is an example of a real application. Not super intuitive if you are not taking physics, but I hope this helps to make things more obvious or more intuitive. Then we are moving on to vectors or cross product, vector product or cross product. The terms again are interchangeable, like dot and scalar product. In this case is denoted as a cross b with a multiply symbol between, and this means ab sine theta, and now it has a direction vector. Okay, C is a unit vector perpendicular to both A and B. It's quite important because in this case, because there's a C, we will notice that later, in fact it's right here, you cannot just simply write A cross B equals B cross A. In fact, you will end up with the negative of it because there's a direction involved now. Mathematically, it will be evaluated as this. For context, this line bracket here means determinant, to calculate the determinant. I believe most of you should have studied matrices previously in secondary school, yeah. So this just tells you this is a determinant calculation. And if you remember, for a three-dimensional determinant, you expand it out like this in the form of two-dimensional determinants. And for this, we get y1, z2 minus z1, y2. And this is how we calculate. It's here. Okay, ABCD is the determinant of the 2 by 2 matrix and is equals to AD minus BC. So here, it looks very daunting and intimidating, but actually just try to remember it as much as possible. Now if you're wondering, how do you remember from, let me erase it, it's looking a bit messy. If you're asking how to remember from this step to this step, okay, from this step to this step is quite straightforward. It's just the unit vector I, j, k, we arrange them. Then the x component of the first vector, y component of the first vector, and z component of the first vector, and then everything of the second vector is here. But from this huge determinant to this determinant here, to this expansion here, it may not look so straightforward. But how we remember it is, we first write out ijk. Then we see for I, right? For I, we block out this, and we block out this, and we take this as the determinant. We take this for the next step of the expansion. For j, similarly, we block this out, and we see that we have the x1, x2 here, z1, z2 here. So we just block out the column and the row that they are involved in. And finally, for k, it's the same thing. We block this one out, we block this one out. This x1, y2, x1, y1, and x2, y2 is what we see here. Okay, so for cross product, I think the hardest part is actually probably just remembering this. There's another method that some of you may have learned before, called the shoelace method. Basically, you extend out this determinant out by another 2 more columns, and then do the shoelace like this, so on and so forth. That also works. But I think it's a little bit messy, so just use whichever works for you. Okay? A visual representation of the vector product can be seen here. Notice that here when we do A cross B, we are taking it as A must be clockwise from B must be clockwise from A, and the resulting C points inwards. Okay, so this is just a convention. We need to be particular about it, because if it's in the other direction, if it's B cross A, it will be pointing out of the page. We are essentially finding the component of A perpendicular to B's direction. So very similar to before when we are doing the scalar product. Scalar product is like we are finding the component that is in the same direction as the other vector. Whereas in this case, we are kind of finding like what is the component of the vector that is perpendicular to the other vector. Okay? And in this case, because there's 2 possible ways to be perpendicular to, there's only one way for you to be in the same direction, but you can be like perpendicular in this way, right, as well. So it's that's one way to think of why you have a vector at the end. Okay, so properties of the cross product includes not commutative, which I've mentioned a few times, and it is still distributive. So if it's a cross B plus C, you can write it as A cross B plus A cross C. If A dot B equals to 0, it suggests that either of the vector is 0 or they are parallel, because previously we said that dot product is testing how parallel they are, and cross product is like how perpendicular they are. So if they are not perpendicular at all, then they are 0 lah. Of course, mathematically you can also see that sine 0 equals 0. Okay, if they are parallel, then their angle between them is 0. So sine 0 equals 0, and this is, yeah. Yep, and finally, if A cross A is equals to 0, A cross A will be equals to 0 because there won't be any component of it that is perpendicular. Unlike previously where you have A dot A equals to the magnitude squared. And finally, scalar multiples can also be removed, because once again, it's like we are just scaling the vectors. It doesn't change the operation. For cross product, it's very important because you can now find the normal of a plane. When we see that a plane, this is very important for the next part, the second part of the vectors, okay? So when we have a plane and we have 2 vectors on it, let's say we have A and B that is on the plane, we can do a cross product of it, and the resultant vector will be pointing in the normal of the vector. Okay? This is important for the next section, and is important. Gaining an intuition of why this is the normal is super important. Next. Oh yeah, so as for why this is perpendicular is just that way, because we the resultant, when we calculate it this way, will result in a vector that is perpendicular. This is one of the properties. Okay, so when we do a cross product, the resulting vector is perpendicular. Next, we can find the magnitude of a component in one vector perpendicular to another vector b. And this is pretty much finding this length here. So at the end of the day, when we try to find the length of how, like this perpendicular length here, we need to remove the vector form because the perpendicular length is not a vector. So then that's why we say that the magnitude of the perpendicular line is found to be the magnitude A cross B hat. Remember you need the hat, because if not, then it's a... Okay, let's just write this out. This is how A cross B look like, right? And we need the hat because it's basically dividing this by B, and this will cancel. And we need the modulus, the magnitude, because that will remove this vector here. And then we end up with A sine theta, which is what we are looking for here. Okay, and that sums up the chapter of vectors, part 1. I hope this was helpful for you, and happy studying.